Stressful when you weren't here.
Yeah, I will be here.
Hey,
That was stressful.
you
I will
can't
be
go
here.
snowboarding.
I know.
I know.
I said I want to. I will be here Monday.
I guess I
All right, let's get started. I want to start with, right at the end of class last time we were rushing through the end of this problem. I want to summarize one thing with this Lagrange problem here. And this problem here, we have this three variable function subject to this surface. And at the very end, I made a comment that if x was 0, we didn't know what y was. And I want to look at that more carefully to make sure that that's true, or make sure that it's maybe not false. So if we look up here, so we had done, to refresh your memory, we did the gradient of the function f, we did the gradient of the constraint, and we got this stuff in here. And focus your attention right in this area. So we said that either, we had a couple of options here. We said we could divide by x, and if we divide by x, then that means that we have to assume that x is not 0 in that case. And then when we went back in and assumed that if we take a look at that, what if x is 0 was our issue down here. So what if x is 0, what if y is 0? So those came from these up here. If we divided by y, we assumed that y was not 0. But what if y is 0, what if x is 0? And I said that if x is 0, or if y is 0, I said that we couldn't conclude what the other variable was. That's not actually true. Look right here. If we assume that x is 0, so that's from this equation, whenever we have a system, we solve one equation and then plug it into the other. So if we assume that x is 0, then we jump down to the second equation, and what would be true if x is 0 for the second equation? Is there a prediction about y?
Y equals 0.
Y would have to be 0 also, so that was my bad there. And if from this equation we assume that y is not 0 when we divide it out, but if y is 0, we go up to the top equation to see if it predicts what x has to be. And what does x have to be in the top equation? If y is 0, x would have to be 0. So my mistake right here, these two, if x is 0, y does have to be 0. Z is still 1. Well, we'll check. I'll show you. And then also there. So then we go back up to our expression over here. So if x is 0, if y is 0, that forces the z value to be 0. So that's all true. 1. If x and y are 0, z is 1. And then we have to go over to our function and plug in our critical points, our Lagrange critical points. So if we did a 0, 0, 1, the function value would be -1. So down here, these guys are actually -1, both of these values. -1, -1. So we just have to talk about our conclusion. So if we had our 4 critical points from last time, our 4 Lagrange critical points that were totally fine, and then these extra 2 Lagrange critical points. Once we have all of those function values we compare, what's the max?
-1.
Yeah, negative. That's going to be the min. That's the least.
I said half really quietly. I'm sorry.
Oh, sorry. And then these guys are all the Lagrange maxes because that's bigger than this. And then so there's the min right there. So in this example, we have 2 locations where we have our minimum value and 4 locations where we have our maximum value. All the other function values will be in between those 2 values. So -1/2 is going to be our max, and -1 will be our min. Everything else on the function will be in between. So yeah, sometimes analyzing those systems can be a little hectic. So let's go ahead and finish up the problems, and then we'll go ahead and do some of these review questions from 12.7, 12.8. All right, so minimum distance to a plane. We did a problem like this just last week where we were doing the minimum distance to, I forget what, a cone or a paraboloid or something. And we did it without Lagrange multipliers. So you can do this without Lagrange multipliers. You absolutely can. This one would turn into a little bit more work if you don't use Lagrange multipliers. The one that we did before, we had, I think it was a cone actually, and you could substitute the cone equation into the distance formula really easily, and it worked out totally fine without Lagrange. Here it would be a lot messier. So we're going to do this one with Lagrange. So this is our constraint. That right there is our constraint. That's what we usually call G. We need to build a function that measures the distance from the point -2, 5, 1. So the distance formula will be the function we are looking for. And we'll do x minus minus 2, so x plus 2 squared plus y minus 5 squared plus z minus 1 squared. And all of that's to the half power, the square root of all that. And then last time we said, well, you could actually square both sides and get that d squared is equal to just the letters over there without the square root. And we're going to create a new function then. And I might as well just square it all out. So this new function is the distance squared function. And minimizing distance is the same as minimizing distance squared. We will have the same exact ordered triple. A point that minimizes distance will be the same point that minimizes distance squared. So that's going to be our W function. That's the function we're trying to minimize. Obviously, we can combine the constants there. So that is the function we're going to minimize. That's our function. Our constraint is right there. So let's go ahead and figure out what del W is. So del W will be 2x plus 4, comma, y squared, whoops, 2y. 2y minus 10 and 2z minus 2. So that is the gradient of the function that we're trying to maximize or minimize, in this case minimize. And then the gradient of our constraint, 2, 3, 6. So we usually call that del G. I said 2, 3, 6. 2, 3, 6. All right, so any question up to that point? Yeah?
So you said that we're minimizing the distance formula using the point because that's what we want to have the smallest amount of? Like
Yes,
the distance.
so we created the distance from a random point over
Okay.
to the
That was redundant.
-2, 5, 1.
Okay.
And then we're going to minimize that subject to the plane.
Okay, so it's not the plane that we're minimizing, it's the actual
It's the
distance
distance
between
point,
the
yeah.
point.
So if you imagine your object, if you imagine a plane and you imagine a point, you can imagine finding the distance between any points on the plane and our given point P. So we want to minimize that. We want to find the least of all the possible distances to the plane.
Okay.
So we're going to minimize the distance formula subject to the equation of the plane. So last time when we did that cone problem, one of the things we observed was that, oh yeah, we have to somehow include the plane or the object into the equation. So at first we started differentiating this before we incorporated the cone in that case into it.
Or the Z.
The Z. And here the way we incorporate it in is using Lagrange instead of using the other technique that we used, which was the second partials test. So here we get our system of equations. So our system is going to be, and we can put the lambda with either one, the del F, or in this case del W, or with the del G. It doesn't really matter. Usually it's kind of cleaner to put it with the one that's simpler. So I'll put it with the del G's. And then we use our constraint as our final equation, and that was 2, 3, 6 minus 10. So 2, 3, 6 equals 10. Let's put the 10 on the other side. Okay, so those are our 4 equations. We have 4 unknowns. And one thing that we notice is that this system is way easier than the last Lagrange system we saw. It's going to be very easy to solve for x in terms of lambda, y in terms of lambda, and z in terms of lambda, because x, y, and z all have just a first power. So it's way simpler than the other ones where we had squares and cubes and things.
Is that what we should be doing though? Is solving in terms of x, y, and z?
In this case, it will be easiest because if we solve this equation for x, the second equation for y, the third equation for z, we can then plug into the fourth equation and figure out what lambda is. And if we know lambda, then we can back substitute to get x, y, and z. So in a case where it's all linear, it's simpler to solve for lambda. With the other problems, it didn't make sense to solve for lambda because of the way the systems were unfolding. But if everything is linear, then it makes sense to solve for lambda. So up here, we're going to say we can divide this by 2. We can say that x is going to be equal to lambda minus 2 if we divide by 2 and subtract 2. This equation will solve for y. So we're going to add 10 and divide by 2. So we're going to get that y is equal to 3 over 2 lambda plus 5. Third equation, we divide out a 2 and then add 1. So we're going to get 3 lambda plus 1 is equal to z. So because they're all linear, we can solve for x, y, and z very simply. And then we plug those into our constraint. Plugging those into our constraint down here, we're going to have 2 times the quantity lambda minus 2 plus 3 times 3 halves lambda plus 5 plus 6 times 3 lambda plus 1. And that's all going to equal 10. So that allows us to solve for lambda pretty simply. Distribute, collect like terms, so we'll just keep on trucking. So we have a linear equation. We get 18, 19, 20, 24 and a half. Let's write it like that for a minute. 21 minus 4 is 17. We subtract 17, so we get a negative 7. That's 49 halves. 49 halves. And that allows us to find a lambda value equal to negative, we can divide out a 7. So we're going to multiply both sides by 2/7, so we get negative 2 over 7. That'll be our lambda. And then we just back substitute to figure out x, y, z. So there's only one solution. The only solution there is, plug in negative 2/7 right here. We have negative 2/7 minus 14/7. So negative 2/7 minus 14/7 is what, negative 16/7? Negative 16/7. Plug it in here. The 2's cancel, so we get negative 3/7. Negative 3/7 plus 35/7 looks like about 32/7. Plug it into the last one. We get negative 6 over 7 plus 7 over 7, so that's 1 over 7. So that is our point that is closest to the plane. That will be our point. So in this case, Lagrange multiplier with distance to a plane, solving for lambda makes the most sense. Let's do a cone problem, unless someone has a question on any step there.
Question.
Yeah?
So back a while ago, you said that we couldn't just find distance between two planes by finding the distance between their z components, but you have to do it like this.
That would be a little different yet still, because if you want to find the distance between two planes, you'd have two constraints. So you'd need a more fancier Lagrange multiplier problem if you have two constraints. The way that you would do the distance between two planes is to use a projection vector. So if we have plane 1 up here and plane 2 down here, we can pick a point in each plane, and then we can find the normal vector for the planes. We can find this displacement vector, which we would call v, and then the distance between the planes, d, will be the magnitude of the projection of v onto n.
But you couldn't do it with this Lagrangian system?
Not with just one constraint.
Gotcha.
Yeah. So we could. That's how we would do projection distance between two parallel planes. Okay, so another distance problem with a cone. Same idea. We're going to get del f. We're going to use the same type of thing that we did above. So we're going to use the distance formula. And then we'll square both sides. So we're going to have x minus 1 squared plus y minus 2 squared plus z squared. So that's the function that we want to minimize. We can call it w or f or whatever we want to call it. I'll call it w. Square it out, we get x squared minus 2x plus 1 plus y squared minus 4y plus 4 plus z squared. Figure out the gradient of that function that we want to minimize. We'll get negative 2x minus 2, 2y minus 4, and 2z. And then the gradient of our constraint is the cone.
Why did you get negative 2x?
That should be positive, thank you. Positive 2x. And then for our cone, we're going to create this function g, and it doesn't matter which direction we subtract. It'll all come out in the wash. So we'll make g the cone. And then the gradient of g looks like negative 2x, negative 2y, and positive 2z. So we have our two gradients. We want those to be parallel. So we're going to set up our system now. And we're going to have 2x minus 2 equals minus 2 lambda x. We're going to have 2y minus 4 equals minus 2 lambda y. And then we're going to have 2z equals 2 lambda z. And then we have our constraint equation, z squared equals x squared plus y squared. So we've got that. And that third equation, that tells us what lambda is. That tells us lambda's got to be 1. So here, we know that lambda is 1. And then what that does is sort of give us some other equations up here. If lambda is 1, then this top equation, if lambda is 1 and we divide by 2, we end up with x minus 1 equals minus x, which tells us that 2x is equal to 1, which tells us that x is equal to 1/2. In the second equation, if we plug in lambda equals 1 and divide by 2, we'll get y minus 2 equals minus y. So that will give us 2y is equal to 2, so y is 1.
2y equal.
2y, yeah, 2y equals 2. That allows us to go down to the third equation. We have x, we have y, so now let's find z. To find z, we have z squared is equal to 1/4 plus 1, which is 5/4. So that tells us that z is equal to plus or minus the square root of 5/2. And that's it. We're done. We found our two ordered pairs. So our conclusion is 1/2, comma 1, comma plus or minus root 5 divided by 2. So those are the 2 points that are closest to the cone. Yeah?
Why does it not work to find z with your third equation?
How can we find z with that third equation? 2z equals 2z.
Okay.
So it's an identity, so there's no
Okay.
way to isolate z
Okay.
given an, it's not, that equation doesn't give us a dependence on x and y, so we can't get in there to get z. But that fourth equation gives us a dependence on x and y to figure out what z is. So we have to go with that fourth one. All right, so those are the two closest. So Lagrange multipliers for the distance is pretty reasonable question, you know. So if I were to give you a 3-variable function, it would be this type of one where you've got 3 variables and well, the distance formula is the function that you're minimizing. So we're trying to minimize that function. I won't give you a 3-variable one like we had just a minute ago because it's too hectic. Something has to be linear to make a 3-variable one reasonable for a test. Those nonlinear ones are too hectic, too much work.
So that's the type of problem that we should.
That's a totally reasonable question.
Okay.
Yeah, distance formula with Lagrange where
Yeah,
you're dealing with a linear thing.
I'm not
Yeah.
okay with that.
That's reasonable.
Those aren't.
Those aren't too bad.
I was gonna say,
Those aren't too bad.
yes, for sure.
All right, we've got one more question in 12.9, and then we can go and start doing more review. We have an absolute max-min problem. One thing I want to point out again, look for those T's. If there's a T up there, that means you're going to have to use technology at some point. So let's go ahead and go through this one. And the key here is that we have a function that's defined on a closed and bounded domain. So we are defining this function, this surface, we're only going to consider the function values on that closed bounded disk. And that means there has to be an absolute min, there has to be an absolute max, because it's on a closed bounded domain. Always the case. Closed bounded domain, there is an absolute max, there is an absolute min. And there has to be one of each. So first we're going to look, we approach this twofold. We look interior first. Interior, we have a 2-dimensional region. And in that 2-dimensional region, we're looking for 2-variable critical points. So that will use the second partials test on the inside. On the outside, on the boundary, that's going to turn into a 1-variable problem. So any critical points that we find on that edge will be 1-variable critical points. So we have 2 different things going on. So first we're going to look interior. So interior, we go up here, we do our partials. When in doubt, start taking derivatives. So f sub x looks like that. F sub y looks like 2y plus a minus 3. Then we find our critical point, if there is one. I know there's only one possible here because it's linear. So we set both of those equal to 0. And when we set that equal to 0, we get that x is equal to -2. If I set that equal to 0 and solved properly.
I don't think you did.
I might not have. 3/2. So yeah, that looks more like -1/2. There we go. That looks a little better.
Okay.
Okay. So is that truly a critical point in this domain? No. This domain is restricted to be just a unit disk. And since we're dealing with a unit disk, we see that this point is exterior to that unit disk. So this would be a critical point if we had a larger disk as the domain. But for this particular disk, that's not going to fly as a critical point, as a 2-variable critical point. So what we conclude then is that therefore there are no 2-variable critical points in the disk.
Oh, so if 3/2 isn't gonna fly, then -1/2 is part of the 3/2. So
Yeah,
then-
so that's an ordered pair, right? That's
Oh,
up
okay.
here, and that is not in the disk. So therefore, we're not even going to consider it. There's no way the function value at a point exterior to the disk can tell us what the absolute max or min is on the disk, because it's outside of it. Yeah?
I think I remember my question. So is that always the case? You can use the 2 or the second partial derivatives test for the interior of everything, does that apply to like every problem?
Yes,
that we've
all
been
the
doing?
maximum problems we've been doing.
And then it's the same with the boundaries on the outside. You can't use that for the
Right.
boundaries.
Second partial test is only for the interior. For the exterior, we have to analyze edge by edge, or the whole circle at once if we parameterize it with theta.
Oh.
Or if you don't parameterize it with theta, you could let it be, you could go the y equals square root method, but then you have to remember that there's hidden
There's hidden.
boundary points. So if we go with the parameterization method, we don't have to worry about any hidden boundary points. So the way we're going to parameterize this
The interior to see if there's any
looks like that. That will be the edge. That's just the boundary of our disk. It's the unit circle, excluding the inside. So the absolute min and absolute max have to be on the boundary here. They're not on the inside.
So because there's not a bigger radius, the radius is just 1, that's why you don't have a coefficient in front of those? Okay.
Yes, yes,
Our cosine.
exactly. Because the radius of the radius of that disk is 1, so we have a 1 cosine and a 1 sine. If the radius was 4, we'd have a 4 and a 4. Yeah,
And we test the boundary points by.
doing this. So we parameterize that, and then we're going to plug those into the function to create a function of one letter, namely theta, right? So we're going to create a one variable function. So this function that we're about to write down gives us the value of f on the boundary as a function of theta instead of as a function of x and y. So if we look at an ordered pair on the boundary, we could plug the x and the y into there, but then we're thinking of it as a two-variable function. This gives us an alternate way to figure out what the height of the surface is at each of those ordered pairs on the boundary. So, plug and chug. Now, one thing I notice is that on the boundary here, this curve is x squared plus y squared equals 1. So on the boundary, I could take out x squared plus y squared here, and I could rewrite that part as 1. I could consolidate that x squared plus y squared up there, because on the boundary, x squared plus y squared is always 1. Now we could do that. Let's just not do that, though. We'll just go straight ahead with what we were planning.
Like
I'm
why?
gonna get rid of the 2 for that.
Yeah, we'd have to pull off the 2. We'd have to make it x squared plus x squared. So, but we'll just plug in the trig function like we said. That makes,
Oh, so we'd still have an x squared.
yeah, you'd
So
have
that's
an
what
x
you're
squared plus 1 if you did that.
Right.
Yeah. So then this is our one variable function. We have to set that equal to 0. And here we could do the same thing. We'd say, oh, let's peel off 1 cosine squared, combine it with that sine squared, and get a 1. So we would have 1 cosine squared plus 2 cosine theta minus 3 sine theta plus 1. And here's where we have to use technology. There's no way you're solving that without technology.
Can you do that again?
Wait, why
Cosine squared plus cosine squared is 1.
Cosine squared plus
Oh, and
sine
we're
squared.
left with the cosine.
So
Okay,
yeah,
I
so if
see
we
how that
if we rewrite, if we think in our mind this is cosine squared plus cosine squared plus
Okay,
sine
yeah.
squared.
Where'd the 2 go?
But you
No,
plot the
but
2
it's
so you
2
get
cosine
cosine
squared.
squared plus sine squared over 2.
No.
No, you just split the 2.
No, we
cosine
just
squared.
separate it. Just separate it. Cosine squared plus sine squared is 1. So I can think of this as cosine squared plus cosine squared.
Oh, I see what you're saying.
Right, and then we can just take that plus that, and that's going to be the 1 out there.
Gotcha.
Oh, because there's 2 cosines.
There's 2 cosine squareds. So we'll just use one of them for the identity.
So then
Where's
What
the
do
2
you-
still?
the 2 is the
There's 2
cosine squared plus cosine squared is 2 cosine squared.
So that is
It's like 1 apple plus 1 apple is 2 apples. And an apple plus an orange equals 1. So we're still left with 1 apple and 1 1.
Okay.
Right? Does everybody follow
I
that?
got it like 2 seconds
All right, if you
ago.
don't follow it, don't do that. Just plug this into your calculator to figure out what theta is. Don't do that then if you don't see that
So
identity.
then you have to figure out.
Now we have to find theta. So how do we find theta? Well, it said to use technology, so we've got to use technology.
Desmos?
Desmos, simplest way to do it. Let's not go through this next step with the technology because I'm not going to ask you to do that on a test.
Okay.
I'll write up the theta values during the break. What do we do once we have theta?
Plug it back in.
Yeah, we plug it in right here to get the ordered pair, or we plug it in right here to get the function value. So we can either get the x and y and plug that into the original function, or we can take the theta and plug it in right there, and we get we'll get the max and the min.
There's probably going to be multiple of those, though.
We'll find out. I'll do it during the break. We'll write it up there. Will?
And yeah, for those two equations there, pretty much there should be an r in front there, except that r is equal to 1 in this case.
Yes.
Okay, just making sure I
Yep,
remember this
that's right. So if the circle is radius 2, we'd have a 2 in front.
And x squared plus y squared equals r squared.
Diana?
Would you do a problem like this, like on the exam?
Not with technology.
Not with technology, but I mean like where we've got to like like a circle parameterizing it with the cosine sine theta.
Mhm,
We did an example like this once already,
Yes,
right?
yep.
Okay. And so just
Yeah.
like look at that.
Yeah, if I did one on the exam, this step right here would be factorable, and you could get theta without having to do technology.
Okay, and then we would just go through the whole step we did before, like of finding our boundary points and like testing each individual point, like where you test all
Right.
6.
So if we do this, when we enter this into the calculator, if we get 4 theta values, we will then calculate the 4 function values that correspond to each of those thetas. The largest will be the max, and the least will be the min.
Okay, cool.
Yeah. So yeah, I'll write that up during the break though, so we don't spend time on the technology right now.
Would you care whether we kept it in theta or
Nope.
do an order triple or double?
You know, you could, keep it in theta or going to x and y, either one. You'll get the same function value, so it won't matter. Okay, so let's go to some of this stuff. Say again? There are no endpoints. And that's the benefit to parameterizing instead of doing the y equals the square root of 1 minus x squared. There's no hidden boundary points. So if we did do it that way that you're suggesting, if we did say, hey, let's plug y equals the square root of 1 minus x squared in, we would have to test these points separately because those would be boundary points for the substitution.
Yeah, kind of that a weird problem we ran into last week.
Yeah, where we had the hidden boundary points. When we said, oh, x squared is equal to 1 minus y squared. There's hidden boundary points.
You have to find
So
the
if you
interior first.
parameterize, then you don't deal with hidden boundary
Check
points.
the interior first.
So that's why it's better to parameterize. So if you have a circle as your boundary, it's better to parameterize it in, because then you don't have to deal with hidden boundary points. Okay, so let's take a look at the questions that popped up from 12.7, number 1.
Good, I'm doing number 1.
And I don't know if we'll go through.
Yeah, do you want to help me with something?
Okay, so
Oh, goodness.
this guy, Rachel, you're the one that asked this one?
Yeah, thanks for calling me out.
Oh, sorry. No, I'm not. Okay, so, and what was it exactly? I don't know if we want to go through each and every one of these, or if we want to talk about them. So I think you said you had an issue with your third partial derivative?
Yeah, it was so
Okay, so let's think about this conceptually. This is a surface. Because I see an x, I see a y, I see a z. There's 3 letters. So if we have an equation that has 3 letters in it, it's a surface. Simplest surface, x plus y plus z equals 0. You know, a plane. Generalized ax plus by plus cz equals d. So if you have 3 letters in your full equation, you know it's a surface in 3-dimensional space. Now this surface is given to us in an implicit format because we cannot solve for z. Now, we can't solve for z there because z is in the exponent. It's also a coefficient. So we can't isolate the z. So this is an implicitly defined surface. So it comes under itself. It's not a function. Okay, so we know that we have a point that's on the surface. Double check. That point should satisfy this equation. If we plug in x equals 0, e to the 0 is 1. And then y times z is -6 plus 6 is 0. So that's satisfied. So it's definitely on the surface. We're trying to find the equation of the tangent plane. And in general, when we think about a tangent plane, we need a normal to the tangent plane. We need a displacement vector in the tangent plane. And they dot to 0. That's how we find the equation of a plane. So we need 2 pieces of information. we need a normal to the surface, a normal to the tangent plane, and we need a point. Oh, we've got the point. So right now, here's where we are before we try to find the normal. So right now, we're already at this stage of the game. We've already got most of what we're looking for. We already have that much. The v vector is a v in the plane, which is a displacement vector off of the point that's in the plane. So x minus 0, y plus 3, z minus 2. That is a displacement vector in the plane off of that point. So x, y, z is a random point in the plane, and you're imagining these displacement vectors coming off of that ordered triple. Okay, so now we have a surface. We need a normal to the surface. So how do we find a normal to that surface?
Take the gradient.
We take the gradient of the parent function. So we build a parent function that has our surface as a level surface. So the parent function that we're going to build is going to be that. You can forget about any constants. You don't need any constants. So this surface right here that we started with, if we were to plug in a -6 for capital F, that would give us a level surface, and it would give us that exact surface right there. If you plug in any constant value for capital F, you will get a level surface. All right? This is a function of 4 variables right here. Let me restate that. This is a function of 3 variables which lives in 4-dimensional space. So its level objects are surfaces. Right, so this is f of x, y, z. It's a 3-variable function which lives in 4-dimensional space. Just like a 2-variable function lives in 3-dimensional space. If I write f of x, y equals x squared plus y squared, a 2-variable function is a surface. It lives in 3-dimensional space. A 3-variable function lives in 4-dimensional space. Each constant that we plug in for capital F will then give us a surface in 3 space. In particular, if we plug in -6, we get that surface. And the gradient of this parent function will be orthogonal to every level surface. So del F will be orthogonal to every level surface, no matter what constant you plugged in for capital F. This is orthogonal to all level surfaces. So we partially differentiate with respect to x. That's going to give us yz squared e to the xz. Partial with respect to y. That's going to give us z e to the xz. And then when we partial with respect to z, we have to use the product rule because we have a product of z's. So we have to product rule it. So let's come up to the top and product rule it. So we're going to do first, which is yz. So I'm going to treat this as one function of z, and there's the second function of z. First function of z is yz first times the partial of the second with respect to z. Partial with respect to z is going to be x e to the xz. X e to the xz. So that's first partial second plus the partial of the first with respect to z is y times e to the xz. So that is going to be our third component down here for our gradient. You see it?
I see it. This is what was struggling with.
Yeah. Product rule can be a little tricky with partial derivatives. Now, we could factor out a y e to the xz here, y e to the xz, and then that would be multiplied by xz plus 1. Okay, so that is normal to every single surface, every level surface. In particular, it's normal to that one. Now, to force it to be normal to this one at that point, we now are going to plug in 0, -3, 2. Excuse me, 0, -3, 2. Plug it in. When we plug in x equals 0, all of these E things become 1, correct? All of these E things go to 1. Because x is 0, so that exponent is 0. So those are all just 1s, factors of 1. Simple. All right, so first one, we have yz squared. So y is -3, z squared is 4, so that looks like -12. Z is 2, so that's our second component. Last component, let's see, xz, xz is 0. Plus 1 is 1, so that thing also goes to 1. So the only thing left is y, which is -3. So that is the normal vector that we will use. You could multiply by -1 if you wanted. Does not matter if you scale it. So we will take -12 to -3, dot it with this, and we're golden. Now we're back to algebra. Maybe I shouldn't say we're golden.
Yeah, 'cause
That's the hard part. -12x, and then plus 2y plus 6 minus 3z plus 6 equals 0. So we're going to get, I'm going to convert that coefficient. When we write our planes, we like to have the front coefficient being positive. That way we all come up with the same equation. So we're going to have 12x minus 2y plus 3z. And then our constants, we have plus 12 on the left, but if I multiply by a negative, I have -12 on the left, and if I move it to the right, I have positive 12. So that will be our tangent plane. And it's reduced. There's no common factors to cancel out. If there was a common factor in there, we would want to zip it out. Take it out. You're welcome. Any questions on that? So a plane, we need two things. We need a normal vector and a displacement vector, and they have to dot to 0. All right, next. Number 4 in 12.7. So number 4, let's see. All right.
Fingernails also tells how stressed out I am.
You know,
Usually it's thumbs. My hands are big.
This is what I do, is I do like picking,
Yeah.
so that when you can tell I'm really stressed.
Okay, this is about looking at differentials. And when we look at this, they tell us what the surface area of a torus is. That's our surface area formula. And they're asking us to figure out the relationship between little r and big R, the small radius, the big radius, and we're supposed to conclude whether the surface area is increasing or decreasing. So, yeah, that part's the easy part, right? So first what we have to do is figure out what a change in the surface looks like, a change in the surface area. That's what ds measures. So we want to get ds as a function of dr and dr, d little r and d big R. So let's do that. So first we're going to have to figure out what s sub capital R is. We're going to have to figure out what s sub little r. So the partial of the surface area with respect to the big radius and the little radius. All right, so with respect to the big radius, we end up with 8 pi squared capital R. When we partial with respect to big R, the little r squared just goes away. It's constant with respect to big R. The second one, we get minus 8 pi squared little r. So those are our two partials. We can then write ds. ds, that's going to be what we use to measure a tiny change in the surface area. That will be s sub r times dr plus s sub little r times d sub little r. Or s sub little r times dr, d little r. That one.
Doesn't sound like English anymore.
I know. That's why do we have to use Should use an R1 and an R2. That might be easier. Instead of a little r and a big R. Okay.
Big for outer radius.
Yep, the big one's the outer radius. So then we just substitute this stuff in. We can factor out the 8 pi squared all the way to the front. So we're going to have 8 pi squared all the way at the front. And then we're going to be left with big R times dr minus little r times d little r. So that's what our ds, that's what our surface differential looks like. Surface area differential. Looks like that. Now it's just a matter of plugging numbers in. So they tell us if little r increases, so let's make sure we understand what that means. So if little r increases, that means that dr is positive. That means there's a positive change in the variable r, little r. Capital R decreases. That means that d cap r is less than 0. So what happens here then? So capital R is going to decrease. So this thing here is negative. R, the two r's are both positive. So we have dr is going to be negative. What about over here? So it's going to be negative or positive?
Positive.
That's going to be positive. So we have one negative quantity, one positive quantity. Can we tell then
And then
what's going on?
Not necessarily.
Yeah, we can't tell. If this one's going to be negative and this one's going to be positive, we don't know which one's offsetting the other. We don't know what the weighting is. So we're not going to be able to tell. If this one was positive and this one was positive, then we would know that ds is going to get bigger.
Wait, doesn't it have to go negative though?
Yeah.
In
Say
this
again?
case, like the way you've had it set up, if dr is positive, that means rdr has to be, like, because it's subtracting, it's negative. So you got a negative minus a negative, so you're only going to have a negative number.
So negative. Oh, maybe I did misinterpret that. So r is, so decreasing makes this quantity negative, and this quantity over here is
Positive, but then
positive.
there's that negative.
So we're going to have a net negative number. Oh, yeah, good point. So we're going to have a net negative there. So, yeah. So in that case, it does decrease. That means ds has to be negative. Yeah, sorry about that. Good point. Does everybody follow that? So if this quantity is negative, and this whole quantity, including the minus, is negative, that means this whole thing is negative. So that means ds does go down. Yes, thank you. That is true. So surface area decreases. Yeah. Because so it's the same sign essentially. It's all negative, all negative. Yeah, I was thinking, I was analyzing this being negative and that being positive, but I forgot to include the sign there. So this is really a negative and a negative, which makes it totally negative. So negative.
Totally.
Totally negative. Okay, now the subsequent parts give you an R value, and they give you a DR, they give you a little r, and they give you a little dr. And so then you just plug those numbers in.
So they give you two R values and two little R values.
Yep.
Define dr like the change in the R values.
Yes.
Would be the difference.
Yes.
Between the
So
values.
let's suppose capital R starts at 4 and then it moves to 4.03. That would tell us that capital DR is equal to 0.03. So we always do the number that it changes to minus the number it started as. So if little r started as 1 and then it went down to 0.96, then d little r is going to be minus 0.04.
Okay.
Yeah, and so the second part of this, you're just plugging those numbers in and multiplying them all that. Yeah. You can do well with these numbers though. They're so little. Okay, let's take a quick look at 9. See if there is confusion on 9. Number 9. Okay, so this one is identical. Everyone agree?
Oh, yeah.
Let's not go through this one. But the idea is very similar. So you have your S defined as a function of R and H. So you would have to find S sub R, S sub H, and set up the same formula we just set up. And then start plugging in your differences. So when you look here, the little r is going from 2.7 to 2.75, so d little r is 0.05. Here you're going from 0.62 to 0.60, so negative 0.02 for dh. So that one will be done in the same way.
Haley has a question.
Yeah.
Thank you. So I did one of these problems using this, like the percent, it's still percent change, right?
If it asks, this is not asking for percent change though.
Okay. Can
This
we
is
do
asking. This
one of
is
these?
asking for. What's that?
Did we just do one just like this?
Did we just do one? like-
Yeah. Was
We
it?
just
There
did.
is one in here.
Yeah, maybe 8.
I was thinking 12.7.36 is a really good example.
12.7, number 36.
Yeah, well, it's 0.36, so I don't know if it's even in the homework.
I don't know if it's not. Do you want to go through? We can go through one of these if you want.
There is
It's in
a
the study
percentage
plan.
problem- percentage problem in homework, maybe problem 8, I think,
So,
possibly.
so should we go through this one?
Yes.
Okay, we can do it. We can do it. We can do it. It's not too crazy. Okay, so so this guy, we partially differentiate S first. So we have S is equal to pi multiplied by little r multiplied by the square root of r squared plus h squared. So we have that. So complete parts A and B. So all right. So let's figure out what S sub little r is. S sub r, I guess there's only one r here. So
So does that mean you have to do product rule?
product
sometimes
rule,
too?
because we have a product of functions of r. Yep. So we'll use product rule. So we're going to do first times the partial of the second. So first is pi times r. Partial of the second, we're going to have 1/2 the quantity in parentheses to the minus 1/2. So that's going to give us a square root in the denominator. Multiplied by the partial of the inside with respect to r, which is 2r. So we're going to end up with that. Cancel out the 2's, get an r squared. And then S sub h will be the same type of thing. We will partial with respect to h, so we're going to get pi r in the numerator. We're going to have a 2 in the denominator. We're going to have a square root of r squared plus h squared in the... Oh, did I not finish the product rule over there? I might not have finished the product rule
No,
over
you
there. Did I?
did. You did because
Well, yeah,
Because
you
they're gonna
multiply by the
first
2r.
Right, but I did not finish the product rule though.
Plus pi times.
Yeah, we're still finishing this one up. Sorry, that was first partial second plus second partial of the first. So we have to get this extra pi square root thing in there. So that's the total partial.
Okay.
That's the complete
You were just so
partial
excited.
derivative. Say that again.
You were just so excited.
So excited to get to h.
Yes.
Okay, so the partial with respect to h, we are going to have just a regular partial of the square root thing. We're going to have a pi r in the numerator. We're going to have a 2 times the square root in the denominator. And then also in the numerator, we have to have a 2h. So again, we'll get the 2's to cancel. So that will be our partial with respect to h. So that means that the estimated change, we can write ds. So that is the change. That's going to be S sub r dr, so pi r squared divided by the square root of r squared plus h squared. All that, I guess I don't need a parenthesis there. Oh wait, I guess I put it because we have that other term there. So yeah, let's keep the parenthesis. And then pi times the square root of r squared plus h squared multiplied by dr plus S sub h. This one I don't really need parentheses, but I'll put them anyway, just so that we can see everything. And then dh. So the stuff in parentheses in front of dr, stuff in parentheses in front of dh. Now we have all our stuff. Now we have to plug. Let's get our values from up here. So this tells us that r is 2.7, 2.70. and dr is equal to 0.05. The h is equal to 0.62, and dh is equal to negative 0.02. So those are our 4 values that just get plugged in now. So we come through here, plug in the r's, plug in the h's, plug in the dr, plug in the dh, and that'll give you your number. So kind of hectic to plug all that stuff in. What's that look for?
I don't know if it'll work.
It will work, I promise you. I can plug them all in during the break.
Okay.
I don't want to spend time plugging them all in because I'll use Desmos. Write all that stuff out in Desmos and it'll just add it all up for us. We can do it during the break. So that's how you find your DS. Any questions on it? Not too bad. It's not too good, but it's not
Nothing
too bad.
is too good.
Nothing is too good when you have that many terms in your partial derivative. Yeek. Yeah. All right, and then what was the last one? That was, what's next over there? 11. Thank you. 11.
Talked about this one.
11.
Isn't this the
Alrighty.
same exact
Yeah, we
one?
did this one in another.
This is like in a totally different homework, but it's the same one, isn't it?
No, we already talked about this one. in this
Yeah, I had a hard time isolating the R.
Okay, we'll just do the first part of it. We'll isolate R. It's once you see how to do it, it's pretty straightforward. Okay, so if we look at R, 1 over R is equal to R plus 1 plus R plus 2 over R1, R2. Everyone agree on that? So if we get a common denominator over here of R1, R2, we multiply top and bottom by R2, multiply top and bottom by R1, add them up, we get that. And then we flip both sides. So now we have R isolated on the left. And then we're going to do the same thing that we just did we're going to have to find R sub R1. We're going to have to find R sub R2. Both of those will involve quotient rule. So let's at least write those out. So here we're going to have low partial high with respect to R1. Low partial high minus high. Partial low is just 1 over low squared. There's cancellation up there, so we end up with just R2 squared. R2 squared. That one. And the other one's going to be almost identical. We're going to end up with the same form, just in R1 squared in the numerator. So those will be our 2 partial derivatives. And then we'll go from there. So then we'll set up the same way we set up the last one. dr is going to be r sub r1 times dr1 plus r sub r2 times dr2. Should I write that equation down? So dr is the change in r with respect to r1 times the differential in r1 plus the change in r with respect to r2 times the differential in r2. And then we'll plug in the numbers. Same as it ever was. Plug in the numbers. Oh, question.
So the difference between this and like the percent change is like that's dV over V,
Mm-hmm.
and this is just dV.
So the difference is they'd be asking for the percent change in R
Yeah.
versus an estimate of the change.
Is that like accurate what I just said though?
Yes,
That it's
absolutely.
just the
So if
top
we
part?
wanted the percent change, we would do dr over R.
Ah,
So R is thought of as the actual value.
Ah.
dr is the tiny change in R. So if we put the tiny change over the total value, we get the percent.
Times
Light bulb.
100?
So it's just like your grades.
Times 100?
No.
Yeah.
Oh, yeah, if you want to do
I was
it,
trying
put
to
it
do
as a
DR,
percent,
I was
yes.
trying to do this over R.
Yeah.
work.
You can use a
Like
percent
this,
change,
something
yeah,
like
percent
Okay,
symbol.
that makes
Yeah,
sense.
you're right. All right, let's take a 10-minute break, and I'll go back and I'll put those other numbers up on the board for those that really want them so desperately.
Okay. You do that.
Okay, I will do that.
Yeah, we'll go through that right after the break. Yeah, we'll go through the section by section, important formula, important formulae.
You never finished these 2 minutes.
Oh, yeah, yeah.
Oh, we gotta
So
do
I
that
would
again.
really like if you see this one, but yes, this
That
one.
one's not bad, right?
I struggle
Let's do them both right now.
but yeah,
Do it.
those would be
Yeah. We have the time, I think. Stop that thing. 12H. 12.8.
So are you the youngest? One.
Or they call him my big little brother. He's 30. But he calls me when he has a flat tire.
When he has a flat tire. That's so funny.
Are you listening to that?
I just heard that.
Gotta help out big brother.
What else you know what you're talking about? That's when they all ask me for all the, I don't know.
I don't know anything. I could say this.
All right, so 12.8, this is number 2.
Oh, this is a good one.
Fine, oh, so good.
Oh, so
So good.
Oh,
So use the second partials test to determine whether each critical point is max or a min. Okay, graph it and
Is this
confirm
number
it.
2?
Number 2.
Okay.
Number 2.
I think so.
Okay, so that's a surface that lives in 3-dimensional space. If we want to find critical points, we figure out where the partials are simultaneously 0 or where 1 is undefined. So let's go ahead and figure out our partial derivatives. Partial with respect to x, we're going to have a 1/2 quantity to the minus 1/2. So we're going to have a 2 in the denominator. We're going to have a square root of the whole thing in the denominator. And then we have to take the partial of the inside with respect, that's an 18, with respect to x. So partial of the inside with respect to x looks like 2x minus 6.
Can we cancel the 2?
Cancel out a 2. Seems like a good thing to do. So that 2 will go away, that 2 will go away, and that will turn into a 3. Figure out f sub y. And then ask ourselves, where are these simultaneously equal to 0? F sub y in the numerator, we're going to have a 2y. In the denominator, we're going to have a 1/2, which puts a 2 in the denominator, times that whole thing. All right, so there's where we're at with our partials.
I think I should just cancel out the 2's in there too, so that you y over the
Yep.
square root.
I like that idea.
It is. You just have to find where it is.
So we're going to set them each equal to 0. The only way a fraction is 0 is if the top is 0. It's the only way. So when we set these to 0, f sub x equals 0. The only way that's possible is if x is equal to 3. Set f sub y equal to 0. The only way that's possible is if y is equal to 0. So this implies that the critical point, this is a 2-variable critical point, is 3, 0. That is the only critical point. Now, we have to decide on whether, so it says to use the second partials test, second derivative test, to decide if it's max or min. What do you think intuitively? If you plug in 3, 0 here, plugging in 0, the y goes away. Plugging in the 3, you get 9 minus 18 plus 18, so you get square, you get 3. What do you think? Do you think it's going to be a max or a min? Any ideas?
You mean the x, if the x is, like if the 3 zeros is max or min?
Yeah. So that's telling us that we have a critical point at 3, 0, so it's going to either be a max, a min, or a saddle point. Do you have any intuition?
I think it says confirm the result of the graphing utility.
Can we get a sense of, let's do this before we do anything else. It's always good to know what the surface is. It helps if you can, and this is pretty easy. So if we square both sides, we have z squared equals x squared minus 6x plus y squared plus 18. So I'm going to complete the square. I didn't give myself enough space there, but I'm going to complete the square in x. Divide by 2 and square. If we divide by 2, we get -3. We square, we get 9. So we need a 9 there, and then we need a -9 over there to offset it. So we'd have z squared equals x minus 3 quantity squared plus y squared. 18 minus 9 is 9. So we have that. Okay. So that is essentially, or it is exactly, a shifted one of these. If we wrote that,
Oh, is it a shifted cone?
it's a shifted one of those.
Is it a cone?
So is that a cone? Let's double check. If you let x be 0, you get a pair of lines. If you let y be 0, you get a pair of lines. If you let z be 0, you get a point. So it's definitely a cone. Now this also started out as a square root, so it's going to be the upper cone. So that's what it's going to be. It's going to be an upper shifted cone. Upper shifted cone, and the little intersection point, whatever we want to call that point, that vertex point, is going to be at 3, 0.
What's going on there? You've got y squared plus some
Blob?
blob, then minus 9, and then the minus 9 becomes a plus 9 down below.
So 18 minus
Okay.
9 is 9. Is that better?
I thought you like decided you didn't
So
want that anymore,
blob
like,
minus
scribbled
9
it out.
equals 9 means blob is equal to 18. Right? Okay, so at least we kind of have a sense of what's going on, right? We know that we're dealing with an upper cone. So that just gives us some insight into what's going on. So we now can do the second partials test. We're thinking about a cone. Do we think it's a max or min now?
Or a
Oh,
min, I
man.
guess. I thought it was.
You're right, it's going to be one or the other.
No, but I thought it was upper.
So it's the upper cone. So does the upper cone have a max?
It does not.
No,
Right.
it's a min.
Right, it has a min.
Right there.
Oh, that's right, 'cause it's this way, it's the hourglass. I was thinking.
All right, so let's see if we're right. That's at least our intuition. That's kind of what we're assuming. Okay, if we plugged in the 3 and the 0 there, did we conclude what our value was going to be? If we plugged in the 3 and we plugged in the 0, we got 3.
3.
Just 3, right? Value of 3. So f of 3 comma 0 is 3. We could plug in other values too to see if we get a sense. Like if we plugged in the origin, what are we going to get?
Square root of 18, which would be 3 squared root 2.
So we get 3 squared root of 2. Is that bigger or smaller? So right there, that kind of gives us a clue without touching the second partials test. So we definitely should be coming up with a min. Because we just found a nearby value that had a higher z value or higher f value, higher function value. So we know we're coming up with a min. Okay, and the only reason I would want to do that is just because we can, because this is a function that we can kind of get a sense for what it looks like. Okay, second partials test. We have to take the partial derivative of this with respect to x, that with respect to y, and then we have to do our mixed partials. That might be another reason that we want to do this one intuitively, because the partial of this with respect to x is going to be pretty ugly. Yeah?
Are you gonna give us something this ugly on the
No.
exam? Okay.
Thanks.
Just had to ask once.
No. Taking this, I will not give you something where you have to take the second partial with a quotient rule and a square root.
Yeah,
Right.
I just used
That's
the
just-
calculator.
Just one or the other.
Yeah, you
Just one or the other.
I- Yeah, just one or two of the three. Yeah, but that's just a little, that's too much work to find it, just to get to the second partials test. The concept is, do you know how the second partials test works? So I want you to be able to find f sub xx and f sub yy pretty easily so that you can then apply, if you get a negative d, what happens, a positive d, what happens. So yeah, I wouldn't give you one that's complicated. That said, we know this is a min based on a couple of analysis points. Do you want to go through that partial derivative?
No.
I will not give you one that hard, I promise.
I don't know if we could just plug this partial derivative into an online calculator or something. I'd like to go review how to use the results from that again.
Say that again?
Yeah, so if we can just kind of skip through going through the partial derivative test by just plugging that into a derivative calculator or something. I'd
Right.
like to finish it up anyway, just for practice.
Okay, we'll look at it right at the end. We'll go through some other ones right now, and then we'll look at that. We can talk about that right after class. The moment it ends. Okay, so that was 2. Yeah, we won't spend time doing stuff that definitely won't be on that test that's coming so soon. All right, what did we set 4?
Oh, that's a question I need to ask.
4.
Quick question, you don't have to go back, but if for those second partials, like for f, x, and y, if they're negative, that's our concavity.
That's our concavity. So if fxx and fyy are both negative, that means that it's concave
Or no, sorry, down.
concave down, so you have a max.
Yeah,
So if they're both positive, you have concave up as
Okay.
needed. All right, so was this the one on there? 4? All right, this says that we've got a box, blah, blah, blah. Okay. So this one, we have, we have a formula here. We've got some sort of box. Let's get our quantities labeled just so we have a sense of how the different variables relate. All right, so we have the length plus the girth totaling no more than 126. So let's call the dimensions, I don't know, x, y, and z. How about that for you? X, y, and z. So that tells us that, which one do we want to be length? Y, I guess. So we need to have the girth around this is going to be x plus z multiplied by 2. So we're going to have 2x plus 2z plus y has to be less than or equal to 126. Find the dimensions of the box that maximize the volume that can be sent. So the volume is going to be x times y times z. Maybe we could even do this. This one's a little different than the one I looked at before class. And the one we looked at, the one I looked at before class, we were maximizing a volume. Let me just think for a second whether we could do it with a g and not break it apart into x and z. Could we do it with just girth plus length? Would that work? Find the dimensions. It says find the dimensions of the box, so it feels like we can't. It feels like we should. Okay, let's just keep going with this. Okay, so the maximum that we can have here is 126. So this gives us a relationship between x, y, and z. So we could solve for one of the letters there, plug it into the formula, use our partial derivatives, and go from there. So let's solve this one for, what letter do you want to solve for?
Y.
So the biggest this can be is 126, so we'll treat this as an equality for the largest possibility. So 126 minus 2x minus 2z. We're going to plug that in down here so that we get our volume is equal to x times that times z. So we're going to have 126xz. And then we're going to have minus 2x squared z. And then we're going to have minus 2xz squared. All right, so there's a function of, that's the volume as a function of x and z.
So where did you get the top equation from?
That we were told right here. It says that if we add so the girth is going to be the measurement around, and so the way that I've labeled this is that we're going to have x plus y plus x plus y to go all the way around the box, and then y is going to be the length.
Okay.
So then we have a function of two variables right there. Then we can partially differentiate it. We can get v sub x, we can get v sub z, we can take the partials, we can do the second partials test. So let's go ahead and do that. So v sub x is going to be 126z minus 4xz minus 2z squared. v sub z is going to be 126x minus 2x squared minus 4xz. So those are our first order partials. Critical points are going to be where those are equal to 0. Those, ooh. Eek.
So this wouldn't be on the exam?
No, hold
It's
on.
a finicky problem.
Let me just glance. Do they have a help me solve this on this one?
Nope.
Help me.
No,
They did
Say that
have a
again?
help me solve this on that.
Because it's a cube, we can divide it by 6.
Say that once again, b sub x is what? Yeah, we have the 1x.
6's for the length and the width, or I'm sorry, for the x and the
But-
y, and then.
There's common terms before that.
Yeah, there's gonna be some simplification. I just want to glance, so before we go any further, if they do, I want to make absolutely certain that we're going the right path. Yeah, we are, we're going the right way.
So wait,
Yep.
did you understand what he said about getting?
So finding the partial
Yeah, I think
derivative
you
set to
just
0 is going to be
box
tricky.
like x plus
Okay,
x
that's-
plus y plus
All right,
5. So
confirmation,
it's
finding the
0
partial derivative set to 0 is
times
tricky.
its length. So it's 2x plus 2y.
Okay, so set these to 0.
But there's an x here, an x here, y here.
And
y here,
let's
y
go
here.
ahead and factor out a z in the upper one here. So if we factor out a z, we're going to have 126 minus 4x minus 2z. Actually, we factor out a 2, right? Cancel out a 2. Factor out a 2. Put a 2 right there.
That makes sense. I understand.
Let's cancel out a 2 because we can. So we're going to have 1. What's 126 divided by 2? Like 63. Minus, what's 4 divided by 2? Okay. I think we get that. Equals 0.
2x, you mean?
Divided by 2, so that should be a 2 there. All right, that looks right. Minus 2z, minus 4, 1, okay. Same idea down here. Cancel out a 2 or pull out a 2, pull out a 2x. And we're going to have 2x multiplied by something that looks really similar. 63 minus x minus 2z. 0. All right, we know that x and z can't be 0. We're talking about a box. So those are not options. We can ignore those two parts right there. So the key then is that right here we can solve for z. So we're going to get z equals 63 minus 2x. Down here,
2x minus 63. Add 2x and then subtract the 63. You get 2x minus 63.
I don't think so. I just added z to the other side.
Oh, then you divide off the negatives from the z, never mind.
So yeah, so if we
Yeah,
if we
sorry.
set that thing equal to 0, we'll get that.
Yeah, I forgot the negative z.
Oh, that's fine. So then the bottom one we get when we set that equal to 0. I'm going to get that piece of the screen. Set this part equal to 0. And let's go ahead and write it as, let's solve it for z also, or let's just plug the z thing in down here. So let's come over to the side and plug in the z. So we have 63 minus x minus 2 times the z from above. 63 minus 2x equals 0. And then we should be able to solve this for x. So we have 63 minus x minus 126 plus 4x is equal to 0. That gives us 3x is equal to something. That's minus, so it's 63. So x is 21. If x is 21, what is z equal to? So we're going to go back up to the relationship that we established for x and z, plug in x equals 21. So right there, if we plug in x equals 21, 21 times 2 is 42, and that gives us a 21 for z. 21. Now that we have x, we have z. To get y, we go all the way back to the top right there. y is 126 minus twice the sum. So y is equal to 126 minus twice the sum of those, which is 42. So y will equal 84. What's that, 44? No, that doesn't seem right.
No, it's
42? 42, thank you. All right, 42. So that means the dimensions of the box are 21. Wow. Go
You're thinking like 2 problems ahead.
too fast to think. And were we dealing, I assume we're dealing with inches and not feet.
Because he did X, Z, Y.
Did I do it in the right order? Oh, I didn't do the right order. We should do it this order.
I think you did it in the right order, you just had your X, I think you chose. something different.
Y is
I don't know.
42. And yeah, we know what each dimension is based on what we put above. All right, so that's how big our box is. I guess it doesn't matter if we stand it up, lie it down, turn it sideways. That will be the dimension of the box. So, question. How do we know that that is a maximum? So the whole question said, find the maximum dimension, let's see, find the dimensions of the box that gives maximum volume.
How do we know?
The box is a square?
Yeah. 21, 21 by, well, the front face of the
The
square.
cross section?
Yeah, cross section.
Cross section is a square?
You can plug it in.
Well, because
our
you
X,
can't
Y,
have a
and Z.
minimum.
Boom!
So, because that'd be 0, which
Yeah.
is not a box. So
Right.
if you set the derivative
Yeah.
equals 0, it's gotta be a max.
Yeah. So this critical point, we came up with one critical point. It could correspond to a max or a min. It's got to correspond to a max because there is no min. We can't have a minimum volume. You could always make it smaller. All right, so that's going to be the dimension of our box. And that was number 4. So let's go to number 7, see if there's any issues on number 7.
What if there's like something else, wouldn't it be like the X's and Y's changed around, like 21, 21?
Yes. And that's what I was just saying. It doesn't, if you stand the box up or lie it down or turn it sideways, it will still have the same
Oh, this
overall
one's-
dimensions. 21, 21.
Well, I
Still,
mean, I-
regardless of how you orient it, it's still like 2 sides are 21.
That's always
That's always what we do.
Well, like hardware, it shows us how to do things.
Yeah.
It's okay, we have to do it hardware first.
Yeah, for that problem, because they told us that it had to be in the shape of a box.
Did you like the chemistry yesterday?
That's not gonna matter which way is up.
Yeah.
Find the absolute max, absolute min. Oh, this is a good one.
This,
This is a good one. There will be an absolute max min problem with a geometric shape, so this is a really good one. Hopefully you know how to find the equation of the hypotenuse of a triangle. All right, so we've got this function. It's defined on a triangle. So our triangle has these vertices, and let's just get a picture of this: 0, 0, 0, 2, and 1, 2. All right, so there's our triangle right there. Okay, we'll use the second partials test plus the boundary, test that separately. So for the second partial, so this is looking inside the triangle. We get f sub x is 4x minus 4. We get that f sub y is equal to y squared's partial is 2y minus 4. So those partials. And that tells us that our critical point, our 2-variable critical point is 1, 2. Is that interior?
It's on the border.
So it's not a 2-variable critical point. So it's not a 2-variable critical point because it's not interior. We have to test 1, 2 anyway because it's a boundary on the boundary. So we have this boundary curve right here, that boundary curve, and that boundary curve. These 3 points are end points of the boundary curves. So they have to be tested because they're boundary points of the boundaries.
Oh,
Right.
yeah.
Boundary points of the boundaries have to be tested separately. So we don't consider it a two-variable critical point. A two-variable critical point has to be interior. Has to be an interior point. So if this triangle was bigger, then we would test that as a critical point, as a two-variable critical point. But we're only testing it as a boundary point for the edge. Okay, so now we go to the edges. There's 3 of them. So now we're going to be looking on the boundary. So now we're going to be finding one variable critical points. So let's first consider, let's deal with the diagonal separate. So this side is x equals 0. This side is y equals 2. And then we'll get to that diagonal one in a moment. So x equals 0. We go back up to our function. We plug in x equals 0. So we're going to create a function of just one letter, y. So f of y, when we plug in x equals 0, is going to be y squared minus 4y plus 6. So now we have a one variable function defined on this vertical edge that's giving us our surface values, but only as a function of one letter. We know how to find max mins of one variable functions. We take the derivative and set it to 0. So this tells us that critical point y value has to be 2. We know the x value is 0 because we just assumed it to be 0 to begin with. So 0, 2. Now, is that a one variable critical point? Is it interior to that segment? No. So it's actually not a one variable critical point. So we don't consider it a one variable critical point. Why?
Yes.
Because it is a boundary point. Critical points are always interior to your geometric object. So if you're looking for two variable critical points, they have to be inside the triangle. If you're looking for a critical point on a segment, it has to be interior to the segment. Boundaries of segments are not critical points. So it's that whole, the picture in your mind, if you're thinking about 2 dimensions, you have A, you have B, and you have this type of thing. These are critical points. Those are boundary points. Okay, so the 1, 2, or the 0, 2 is not a one variable critical point because it's a boundary point to that segment. Critical points have to be inside your geometric object, whether it's a region or an interval. We have to test 1, 2, but we're testing it because it's a boundary point. It's a vertex. So now we go to next edge, y equals 2. Back up to our function. We put all the y's to 2 and leave the x's. So 4 plus 6 is 10. 10 minus 8 is 2. So we get 2x squared minus 4x. Was it minus 2? Or plus 2? So we plugged in a y equals 2, so we had 4. We had 10 minus 8, which is positive 2. So now that's giving us our function values along the top edge only as a function of x. So it's a one variable function. So let's see if there's any one variable critical points hidden inside that little interval. If we come up with one of the endpoints, it's not a one variable critical point. Take our derivative, f prime of x, we get 4x minus 4. That means our potential critical point is going to be x equals 1, 2. Oh, 1, 2, that's a boundary point, that's not a critical point. So, not a one variable critical point. Okay, so now we have one extra edge to test. You guys are masters of writing equations of lines down by now. Beautiful, 2x. It goes through the origin, so you know the line is y equals mx. The m is 2, up 2 over 1. Y equals 2x. Algebra conquered. So y equals 2x. Conquered. So now we're going to replace all the y's with 2x's. So let's just see. So if we let y equal 2x, let's figure it out up here. So we're going to have 2x squared minus 4x plus 4x squared minus 8x plus 6. So that's going to be 6x squared minus 12x plus 6, I think. Okay, 6x squared minus 12x plus 6. 6x squared minus 12x plus 6. That is a function of one variable. So the surface values on that diagonal edge are given by this. Let's see if there's any critical points there, any 1 var critical points. 12x minus 12, x equals 1. So a potential critical point would be 1, 2. Nope.
I can't even.
Did you factor? Is that what just happened?
No, I just plugged in,
You took the derivative.
took the derivative,
Oh.
took the derivative, took the derivative, set it equal to 0. Same as it ever was. You've been doing that for semester after semester. Derivative, set it to 0, find the critical points.
This is interesting.
That's a boundary point. So we have no critical points, but we have a bunch of boundary points. So there are no CPs by definition. So we look at our boundary points, because we always have to test critical points and boundary points. So our critical points, none. Boundary points, 3. And we're going to plug those into our function. Our function is that, whatever that thing is. Oh, gosh. So that function, we will just bring down. Oops. Send it to the current page.
Oh, Lord.
Good grief.
What is up with these like mutated images?
All right, there's our function right there.
They melted together.
Okay, now we plug in those 3 boundary points, figure out the high, figure out the low. We're good. So plugging in 0, 0 gives us 6. Plugging in 1, 2, plugging in 1 for x gives us 2 minus 4, which is negative 2, plus 6 is 4. 4 plus 4 is 8. 8 minus 8 is 0. I believe we get a 0. Plugging in 0, 2, 4, 10 minus 2. So this tells us that our max value is 6, and it occurs at 0, 0. Our min, and I should put absolute here. We're talking absolute max, absolute min. All right, so there's our absolute min and our absolute max.
And a local min for good measure.
Huh?
And a local min for good measure?
No.
No.
Local mins can't happen at, like when we look over here,
We can't have it on
for a local min or a local max has to occur at a critical point, and a critical point has to be interior. So we wouldn't, over here, we would not call this a local max. This is an absolute max because we've included the boundary, but it's not a local max. So for a local max, there has to be function values on both sides
both sides, okay.
of the b in this case. So we won't call it a local max.
So what's that extra point?
What's that?
So if that extra point isn't a local min or local max, what is it? What is it classified?
An in-between point. Which point?
It's a boundary, but it's
0,
not.
2.
It could be
Zero,
anything.
2.
So the absolute max occurs at this boundary, at that, at the boundary point.
Yeah, I understand those top two, but what is that bottom one?
It's
Is
just
it
a
nothing?
point.
Oh, it's just an intermediate value.
Okay.
Yeah, we wouldn't call it a local max though,
Okay.
because it's on the boundary.
It just happened to exist at the boundary, but it's neither. An absolute max and absolute minimum.
Yeah, absolute min and absolute max, they can occur inside or on the boundary, but local extrema, there has to be a cushion.
Yeah, I
To-
get that.
Okay.
All right, thank you.
Yeah, so it's just an intermediate value, just an intermediate y value. Yeah.
Are we gonna, I don't think I've come across a problem yet where there was absolute max, absolute min, and a local min or
Mm-mm.
max. Are we gonna come across that?
No, usually we're asking for one, well,
I mean,
I
think it was in the
we,
homework at all.
when we're dealing with surfaces, that's extremely rare.
okay, okay.
When we're dealing in Calc 1, where you had, maybe you had a function that looked like this,
Yeah.
you know, something like that,
Mhm.
there you can have a local max, there's your absolute max. You have a local min, there's your absolute min.
Okay.
But with us, with surfaces, that's much more difficult to create a surface that's got, you know, some multiple, you know, peaks where one is going to correspond to the absolute max. You know, that's going to be pretty rare.
Okay.
And the reason is it's just difficult to build it, but then when you find your critical points, if you're going to have 4 critical points, you're going to have it's going to be very difficult if you do have a surface that has those multiple peaks. Your partial derivatives are going to be complex. They're going to be 4th order. You know, if you're going to have 4 critical points and trying to solve a 4th order polynomial is very hard unless you use technology.
I wasn't sure if I missed something.
No, it's just super rare. They're not going to cook one up because it's going to be so hard to build.
Okay.
Yeah. Is there someone?
I was just gonna ask you to scroll up. You did.
Oh, okay. Okay, that was number 7. So then 12.9, number 2. 12.9, number 2. Let's go. 12.9, 2.
No, we have one more.
Yes, we have. Well, this is
All right, so Lagrange multipliers.
What is this short?
So we have 1, 2, 3, 4, 5. Yes, we have 1.
Good one to review.
3 weeks.
Send to the third page.
Or next exam.
4 weeks till home.
Let's see.
Which is not.
All right, so we have, so again, on the exam I said that for a 3-variable function, if I'm going to give you one, it's going to be something like the distance formula where you're going to end up with stuff that's linear. And you're not going to have to solve a bunch of weird, difficult quadratic type stuff. So let's set this one up. We are going to have our del f, and if it's way too hairy, we'll go on to something else. So there's our gradient for the for the hypersurface. This surface is in 4-dimensional space because it's a function of 3 variables. And then our constraint is a surface, and our del g is going to be, so we're going to let g equal x, y, z. So we'll have y, z, x, z, and x, y. So our setup will be something like 14x equals lambda yz, 14y equals lambda xz, 14z equals lambda xy, and then our constraint was xyz being 5. xyz is 5. All right, 4 equations, 4 unknowns. We'll give it one attempt to see how crazy it might get. If we multiply this one by x, we're going to have 14x squared equals lambda xyz. Multiply that one by y, we're going to get 14y squared equals lambda xyz. Multiply that one by z, we get 14z squared equals lambda xyz. All right, so all those right-hand sides are equal. That means the left-hand sides have to be equal. So this tells us that x squared equals y squared equals z squared. Which tells us that x equals plus or minus y, x equals plus or minus z. Gives us a whole bunch of little sub-conclusions. So now we would have to figure out options here. So if we want to rewrite this equation down here where we have all x's or all y's or all z's, let's write x as a function of y. No, let's leave that alone. Let's write y as a function of x and z as a function of x. So here we're going to have x squared equals y squared. If we solve for y, we get y equals, what? How are we going to write that? Plus or minus x. And then we're going to write z as equal to also x squared z squared equals x squared, so z is going to be plus or minus x. So we're going to come down here and figure out what is going on. So we have x times that stuff. So we're going to put a plus or minus x here and a plus or minus x here. All that's got to equal 5. So when we multiply all that together, we could get x cubed or we could get negative x cubed. So we're going to get x cubed, when all is said and done, is plus or minus 5.
How would you ever get negative x cubed?
If this one was positive x and this one was
Oh,
negative
okay.
x, because there's all
Sorry,
those
my
sub
brain is like
possibilities.
fried.
X could be positive, y could be negative. So then we get x is equal to the cubed root of plus or minus 5.
It's like the stupidest question.
Shouldn't it be shouldn't it be plus or minus the cubed root of 5?
Yeah, either one, because the plus and minus can come to the front. So yeah, absolutely. What you just said is totally, yeah, that's either ways means the same
I mean,
thing.
isn't it like not allowed to do a root of a negative?
Well, it's an odd root.
Oh, okay.
Odd roots are fine. Odd roots are fine. Okay, so now we know that we have a whole slew of points. We have x could be positive, y could be then positive or negative, and z could be positive or negative. So our Lagrange critical points look like this. Plus or minus third root of 5, comma, plus or minus third root of 5, comma, plus or minus third root of 5. So we've got however many of those are. Lots of choices. And we go to our function. Our function was, I can't even remember anymore.
7x squared equals 7.
Oh, 7 times the sum of the squares.
Yeah.
So f is equal to 7 times the sum of the squares.
Did you get the all three or positive or minus cube root 5?
Yeah, those all, because we get right here that x is going to be plus or minus the cubed root of 5, which means z is going to be plus or minus the cubed root of 5, and then up here it means y is going to be plus or minus the cubed root of 5. So we have all those different possibilities. So now we're going to look at our values, and it's not going to matter whether we plug in the positive or the negative because we square these. So what is our function value at any of these points? The function value will be the cubed root of 5 squared plus itself. So we're going to end up with 3 times the same thing. So we're going to end up with 21 times 5 to the 2/3. So that value is going to be the value of the function at each of those critical points. Could it ever be negative?
No.
No. So that's going to correspond then to the maximum values for that function. They're all going to correspond. Where is it mins or maxes? Let's see. If they're all the same, yeah, if they're all going to be the same, do we say they're mins or maxes?
You would just say none, right?
They can be the maximum
Yeah,
and
it is
minimum,
an
right?
If all the values are the same.
There's an option that says no local, right?
It's like if you're the only
You could
one that
just say
competes in
none.
a race, you're first
There's
place
no
and
local
last place.
maximum value, and then you can
If you're the only one that competes, you're first and last?
Yeah. So I'd say that they're both the maximum and
Yeah,
minimum.
that's very interesting. We haven't seen one like that. If there is a local maximum value, what is it? Select the correct choice below. The local maximum is, there is no local maximum.
Could you just go back to the thing and try it?
Yeah, can we just?
Yeah. That feels
big
weird.
But even if they're all the same, doesn't that still mean that they're all local maxes? They could still all be local maxes?
Yay!
Oh.
They're all local
Just say no.
maxes?
Oh.
Yeah.
Nope.
Oh.
It's a min.
So it's a min.
It's a min.
So
How do we know
what did
that?
we say the value was?
21 times 5 to the 3 halves, I think?
Or
2/3.
Was it
2/3.
Yeah, 2/3.
I wonder if it'll take that. Oh, well.
Oh, it will.
Oh.
Okay, so here's how we decide.
Is it
There's-
because all of the variables are positive?
When we look at this up here,
I don't know.
we should be able to analyze.
What is that shape?
No,
Yeah,
we're
that's
facing
what I was
parabola.
Isn't that,
Well, it's a hypersurface, so we can't really
Oh.
visualize it. It's like it's the analog of a paraboloid.
Can't do that.
So we can't do that.
So how do we know for sure that it's a min? Okay, we know that it's a min because we can make x as large as we want, right? We could pick x to be 1,000, and then to satisfy this equation, y and z would both have to be small. But if we can pick x to be 1,000, that's going to make this term very dominant, and then these guys will be close to 0. So there is going to be no maximum if we analyze that, because we can pick x to be as big as we want. We could pick x to be 1 million. And then for this equality here to be true, y and z would have to be tiny, 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 but that's not going to matter over here. When we plug in x equals 1 million, this is going to be monstrous, and these guys will just be even closer to 0. Right? So there's not going to be a maximum when we analyze this. We can let x be as large as we want. It just means that y and z are that much tinier, but that means that we can still get an arbitrarily large function value depending on what x, y, and z are. So that's why it's got to be a min.
so
Can't have
does
a max.
that mean that the only way to prove this would have been like through some proof by contradiction, saying there's no max, there has to be a min? Like, is there
Right.
any way to do it mathematically? without-
Yeah, well, that what I just said we could turn into math. Think of it this way. What about a parabola? If you have a parabola, that's kind of the two-dimensional analog. Parabola, can it have a max? No, it can't have a max because, yeah. But it's squared.
Oh, so it's only gonna ever go up?
Yeah, yeah.
Would we,
Yeah. So that would be our analysis, would be something to that effect. But I'm not going to ask you to be that creative.
what if we took the second derivative? Would that make a difference?
So another possibility is, well, we can't, the second partials test isn't going to work here.
It's not gonna work here.
Why not?
Because second partials test is only for surfaces, right? The second partials test is for fxx, fyy, and fxy, right? We don't have a three variable analog to the second partials test, and I've never seen one. I don't know that there is one. So the second partials test is only going to work if we're dealing with a surface, not a hypersurface.
But, I mean, even if we don't do like the fxx and fy, can we still take a second derivative the way we would have in Calc 1 or 2 to find concavity and
We
blah,
can
blah,
take
blah?
but we have three variables though, so we can't.
You can make it too though, can't you?
Oh, we could make it 2. That's a good point. That's a good point. We could solve this for z and plug it in there, and then we could use the second partials test. That's a good point. If we take this, so here's the way to think about that, is that if we take a hypersurface and intersect it with a surface, we're going to get another surface, and that surface is going to be a function of two variables, which we could use the second partials test for. We don't need to go there. We don't need to go there, but that's a great point. If we solve this for z, plug it in there, then that would give us a mathematical way to show for sure that it's a min and not a max. That would be a very secure mathematical way. But we can just use intuition here, that we can let x be as big as we want it, so f goes as large as we can imagine. So we know it's a min. Okay. All right, so let's see, that was number 2. All right, so let's talk about generality. Can I borrow that for a second?
Yeah.
So if we look at the study guide, the first section, functions of several variables. That, back to the beginning. So there's a range of questions on here to look at. Finding the equation of a plane is going to be the most important thing from section 1. Make sure you can find the equation of a plane. We've done multiple examples. The next most important thing in there, make sure that you can identify quadric surfaces. So that's number 4 on here, but it's the second most important thing. I'm going to try to target a little bit more precisely. So I definitely want you to be able to cross out the x, notice the trace is a parabola or a hyperbola. Cross out the y, notice the trace is a hyperbola or a line or whatever it is. And then identify the quadric surface. So the 6 quadric surfaces. Now, the last most important thing on here is finding the equation of a line. I hope that that is something that is obvious at this point, how to find the equation of a line. So the focus in this section should be finding the equation of plane and getting comfortable with your quadric surface traces. The second section, graphs and level curves, you may have to sketch a few level curves, so knowing how to sketch level curves. And then the first thing on there was finding domains. So if you have a square root function, you know that what's under the square root has to be greater than or equal to 0. If you have a fraction, you know the denominator can't be 0. Yeah?
For the domains, so do you want us to like draw out our domains and then do that that special notation?
The set builder notation?
Yeah.
I'll probably just ask you to sketch the domain.
Okay.
Because it's a little easier in 2-dimensional space to sketch it. Sometimes the set builder notation, you can use that for sure.
I mean, sketch the domain.
Sketch the domain. So if the domain happens to be a disk or something. So like, for example, if you end up with a function that, like this, if you have f of x comma y is equal to 1 over the square root of 9 minus x squared minus y squared. So in this particular case, we have to analyze the denominator, and the only way this function is defined is if what's inside that square root is what?
Well, not 0.
Greater than 0.
Greater than 0. So it's got to be positive. If it was in the numerator, we could say greater than or equal to 0, but if a square root's in the denominator, the inside has to be greater than 0 strictly. So then we get x squared plus y squared is less than 9. So you could sketch this domain.
That's a circle.
The domain is going to be a circle, including the inside. So it's going to be that, but we exclude the boundary, so we would want to make the boundary a dashed dotted line.
So if that was greater or less than or equal to, you'd not do a dotted line.
Right. So if this was in the numerator, we would include the boundary and we wouldn't dash the border.
So if it was greater than 9, there would be everything except for
There'd be everything on the outside.
Okay.
Yeah, which is possible too. So you could have something like, if you have a function like the square root, if you have the minuses backwards, so if you have x squared plus y squared minus 16, that type of thing, then you have to have x squared plus y squared minus 16 greater than or equal to 0. So here, you're going to be on the outside of the circle of radius 4, on or outside the circle of radius 4. So your sketch would be something, you include it and do some sort of thing like that. All that stuff out there.
What if it's not a circle? What if we just get like x is greater than 1, or do we need to do a number line?
Yeah, well, if you get x is greater than 1 and you're dealing with a surface, it actually means a half plane. It would mean if it's greater than 1, it'd be everything to the right of 1 where y is unrestricted. So it would be a half plane.
So how do I sketch?
So if you were going to sketch a half plane, so if you had something like if x had to be greater than 1, or let's say greater than or equal to, so then we're talking about doing something where we just somehow indicate that we're on this side. Yeah. But you can put set builder notation too. Either way, I'll ask you whether to graph it or set builder it.
What are you talking about, set builder?
Set builder is this says it's the set of x comma y. It's the set of ordered pairs.
Okay, I gotcha.
So this is set builder notation,
Okay.
where you would say
Like in the
x is
homework.
greater than or equal to 1.
Gotcha.
Oh, that's
And so here you would do, set builder for here would be x comma y such that.
Mm-hmm.
So, but typically it's nice to graph it just to make sure you understand what the equation or inequality is representing.
Well, we know it's
All right, so section 3, limits of two variable functions. So we had a few examples where you could just plug them in, and if you get a number, then you're done. So the big issue there in with the limits is figuring out when showing that a two variable limit does not exist. So be able to do the two-path process. If you want to show a two variable limit does not exist, you need to show that along two different paths you get different limits. And then that two paths. Well, if you choose two paths that have the same limit, then you may
then you
have to pick a third, but you need to find two paths that have different limits. Two paths with different limits. Polar coordinates, so there very likely could be a problem where you deal with polar coordinates. So trying to find the limit of something, if there's x squareds and y squareds in there, and you know, I don't know what I should be putting in here right now, but stuff.
Just have like an X and Y on the top.
If there's x squareds, y, oh yeah, that's pretty typical. X and y on the top, and this is on the bottom. Yeah, so pretty typical. Something, yeah, let's do that. That's a good one. So something, if you see x's and y's, and you're going to the origin, then you're thinking to yourself, oh, polar is a good option. So x squared plus y squared, if you don't see an x squared plus y squared in there, you shouldn't be thinking polar. But if you see an x squared plus y squared, and it's going to the origin, you should always think polar is a possibility here. So whenever you see that. Okay, partial derivatives. So section 4, be able to find your partial. I mean, now section 4 seems kind of, so easy because we've been taking partial derivatives for a month now. So the big theorem in that section is for non-differentiability. Remember that if a function is differentiable, that means it must be continuous. And if it's not continuous, that means that it's not differentiable. So that's called the contrapositive.
Is that the area where you have non-differentiability?
Yes. Yeah, the non-differentiability. So the types of examples that we saw there, we had a piecewise defined function, and so we would have to analyze whether the piecewise defined function was continuous or not. So the picture for those, if we look in 2 dimensions, it's easier to draw the picture. So if we have something like that, then obviously it's not going to be continuous because the value of the function doesn't equal the limit of the function. In 3-variable space, you're thinking more of a peak, where the top of the peak is maybe taken out and defined to be different than the top of the peak. So then it's not continuous. Or you could have this situation where the function is defined to be the same there, but you have to calculate that. You have to show that the limit and the value are the same. And if the limit and the value are not the same, then it's not continuous, which means it's not differentiable.
Yeah.
Okay, so continuing on to 12.5. 12.5 is kind of, yeah, 12.5, I don't care if you take, so 12.5 is the chain rule. And I don't care if you use the chain rule formula or if you use substitution and then use partial derivatives. That doesn't really matter to me. There's no benefit to just using the pure chain rule formula. The most important thing is that you're able to get the partial derivatives. So the one thing in here that is important is the implicit differentiation, dy dx with implicit differentiation. That is something that is very helpful to understand. And so our formulas, we said that you could find dy dx by doing minus f sub x over f sub y if we're in 2-dimensional space. And if we're in 3-dimensional space, you can find the partial of z with respect to x by doing minus f sub x over f sub z. So these formulas are important ones. So this is in 2-dimensional space where you're finding a derivative, and then this is with a multivariable function where you're finding partial derivatives. So that idea is super important. It's not too dissimilar from what we did when we're finding gradients. You know, it's that same idea. Directional derivative. Definitely there will be directional derivative problems. So make sure the biggest mistake, when you look at the directional derivative formula, the biggest mistake is blowing this part of it. When you're finding the derivative of a function in a particular direction, we use the gradient of the function multiplied by u. That has to be a unit vector. That is the biggest mistake that I see, is dotting with a general vector and not a unit vector. So make absolutely certain when you're finding your directional derivative that you make that a unit vector. It has to be a unit vector.
Yeah, maybe we could just write that vector u divided by the
Length of u?
Yeah, length of u. Make it clearer on our notes.
Yep.
So
Yep.
12.6? Sorry.
Say that again?
Is that 12.6?
That is 12.6. Yes.
So you'll give us a function, we'll have to take the gradient, and then you'll give us some vector, and we have to determine if that's a unit vector or not, and
Yes.
if it isn't, we have to convert it to a
Correct.
unit vector.
Exactly.
Probably a point where you.
Exactly. Okay, so then in that section, there's going to be the steepest ascent and steepest descent type of thing. So you'll be given a function, and it will say, find the direction of steepest ascent, find the direction of steepest descent, and calculate what the rate of change is in each of those directions. So we know that the gradient is going to be the vector that points in the direction of steepest ascent. Minus 1 times the gradient will point in the direction of steepest descent. The norm, or the absolute value, or the magnitude of the gradient will be the rate of change, the steepest rate of change, and minus 1 multiplied by that number will be the rate of change in the direction of steepest descent. Yeah. I'll try.
Just talked really fast.
I talk slow.
It's just a grade.
Wait, you take the gradient, and that's the direction of steepest descent, you said?
Yeah, so del F points in steepest direction.
And then you just take the opposite for the steepest descent.
Yes. So the steepest, I guess I should say steepest ascent direction. And then minus 1 times the gradient points in the direction of steepest descent. And then the rate of change in the direction of steepest ascent is the length of the gradient. So the gradient gives you the maximum rate of change in all directions. Right? So if you know what the value of the gradient is, you know the steepest, the steepest rate of change
At a given point.
at a given point. At a given point. At a given
So
point.
length of the gradient is pretty much just a slope.
Yes, the length of the gradient is the slope in the direction of the gradient.
Okay, wait, one more time. So this, sorry, so this is steepest ascent, minus is steepest descent, magnitude is rate of change. Okay.
Yep. And then
Alright.
minus 1 times the magnitude is the
Minus.
rate in the down direction.
Ah, okay, got
Rate
it.
in the down direction.
Multiply.
All right, and then the next section, we've talked a ton about this already, 12.7, 12.8, 12.9, what we did today. Find tangent planes, find linear approximations, max mins, gradients, max mins, second derivative test, Lagrange multipliers. Yeah, so that all the stuff that we did today, the stuff we focused on today.
Oh my goodness.
I know, it's so exciting. The weather is perfect for studying. The weather is like, I remember last year, the weather was beautiful outside and no one wanted to study.
That's why.
Everyone wants to study now.
Just bake some chocolate chip cookies.
All right, so I will be in the Mass Center Monday morning, 9 to 10:30. If
Oh,
you're,
you better be ready by then.
if you need help, come in there. We'll do. I'm sure we'll have a little Calc 3 powwow.
Yeah.
But be ready by then. Be ready by then. People
Yeah.
are still not ready.
Yeah, don't wait till the last minute though.
That was far when we walked into the session.
Don't do that.
And it was
Don't
like
wait
me,
till the last
Vinny, and like Rachel, we were all like,